All right, so here's my silly example. Suppose you and your roommate have a special coin to decide disputes, including whose turn it is to take out the trash. So you want to examine if the coin is fair and you believe it gives out a larger proportion of heads than it should. You decide to use your knowledge about a sampling distribution proportion to see if he's cheating you. So we flip the coin 20 times. There's our sample size, right? Our number of trials. And we get out 12 successes. So we're seeing a binomial distribution going on, but we're going to use the sampling distribution of a proportion to answer these questions because I want to draw connections between all the different parts of part 6. The exercise about the balloon angioplasty really got us the connection between hypothesis testing and confidence intervals, and this is going to show us how 6.1 is related to 6.3. So our two hypotheses we'd like to test here. Well, we're talking about the P, right? The proportion of heads that our coin gives out. So no matter what, we're talking about that. And we have two options here, right? One is my roommate is innocent. It is a fair coin, right? Because we have to have our equal to and our null hypothesis, and we'll see why in a second. Our alternative is, well, I thought it gave out a larger proportion, so I think that the P is greater than 50%. That means my roommate is a cheater, right? And this is what I want to prove. So we went out and took our sample, right? And we got out a sample proportion of 12 out of 20, or 60%. Was this sample proportion evidence for what you wanted to prove? So this is just glancing here and saying, okay, because you should come up with your hypotheses before you go and collect your data. So it is possible that after you collect your data, you find that you're actually not getting something that supports what you're trying to prove, and therefore there's no point in doing the test. But yes, 60% is greater than 50%, so we have evidence of what we want to prove. Now, really the question is just, is 60% enough evidence? So we're going to use that approximate normal distribution, but means we need to check our assumptions. So are our trials or observations independent? Well, we're flipping a coin. So, right, we've got this. Boom. If sampling is done, it needs to be, we didn't do any sampling. We were flipping a coin. If sampling, okay, we still don't need that. We're flipping a coin. But we do need to check our rule of thumb to make sure we have normality. So in this case, you'll note, remember in 6.1 we had NP, NQ greater than equal to 10. In 6.2 we had NP hat, NQ hat greater than equal to 10. And in this particular question, we have both a P running around and a P hat running around. So it's not necessarily immediately obvious what we should be using, but we should go ahead and use the real P, even if it's a hypothesized real P from our null hypothesis. So if we were to check this one, boop, we would be going, all right, so we had 20 times 0.5, 20, oh, Q is also, they're both exactly equal to 10, so we barely have our rule of thumb, right? But I knew that. That's why I chose to flip the coin 20 times, because I was lazy. And 25 rolls of the dice today was miserable. All right. What are the mean and standard deviation for a sample proportion? So this is where you'd go to your formula sheet. You go to the section where it says bloop, 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 sample proportion, and you'd grab the mean and standard deviation. So the mean for our sample proportion is the real P. So in this case, we don't know the real P, but we do have an initial assumption. We have to say, okay, well, we're going to pretend that the roommate's not a cheater. So 0.5. Our standard deviation is PQ over N, square root of all that. So 0.5 times 0.5 all over 20. Let me get back my calculator, which is missing. Oh, I forgot to do the square root first. I'll have to do it after. Second, square root, second. I don't recommend ever doing it this way because I always have students that stop and give me that as the standard deviation. So I like to do it all at once. 0.1118. All right. So now we're going to see the connection between 6.1 and 6.3. we're going to draw a curve for that sample proportion and shade the probability of getting out a sample at least as great as what we got. So since we had all the check marks up in the first part in part D, we know we have an approximate normal centered at 0.5. When we went out and did our sample, we got 0.6, which is not that unusual, especially when you think about these standard deviations, right? Our standard deviations here, we're not even one standard deviation away, but that's what we're going to be looking at. Now, the other thing is we only had in this question 0.6, but we do have this right-tailed test. This greater than, this right-tailed test tells us that we have a direction to shade. We actually want to shade this way when we're looking at this problem. So we can do two things. We can calculate a z-score to see how unusual 0.6 was. So remember, our z-score is our observation minus our mean, what we observed minus what we expected, divided by our standard deviation. But as I said, we did less than a bunny hop to get from 0.6 to 0.5, so it's not going to be a very exciting z-score, 0.89. So not even one standard deviation away from the mean. And we could also figure out our probability, which you could use normal CDF for. 0.6, E99, 0.5, 0.1118. Oops. .1855. All right, so based on these probabilities, is the coin behaving unusually? So the z-score is less than 1. It's not unusual. And our probability is equal to approximately 19%. That's also not unusual. So what can we say about our roommate? Well, we can't say much of anything. 0.6 is something we would expect to happen, right? This is like us rolling our die. This could definitely happen if it's a fair coin. So basically, I can't prove he's cheating. I'm never going to say he's not cheating because that's what I want to prove, but I don't have enough evidence to go tell him he did something wrong. So H says, well, what if I was really, 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 really crazy and I went and flipped the coin 200 times? I hold a grudge, so that might be something I would do because I'm a crazy person. And I got out 120 or more heads. So my p hat here is still 60%. But we have a much larger sample size, which means our sampling distribution is going to be a lot more narrow, right? Our mean of p hat is still p, but 0.5, sorry. Right, we're still going to use the real p from our hypotheses. But our standard deviation is now divided by 200, and that's going to make a big difference because we're going to see a big drop in that standard deviation. So now, we have 0.0354. So if I was to think about what's happening in my distribution, now when I go out my bunny hops, I'm at 0.53, 0.57, 0.60. So now my 0.60, oops, is actually really unusual in terms of bunny hops. And we could even go ahead and get ourselves the z-score. That 0.6 minus 0.5. But now we're dividing, oops, I need to finish up. Press enter first. Now that's going to be divided by a much smaller standard deviation, 2.82. That's a very unusual z-score, right? By every metric of our z-scores being unusual, that definitely is. And our probability, well, I could bring back our normal distribution thing because I don't want to have to type all this crap again. And change this to 0.035, oops, 54. That is not 54. Probability is now 0.0024. So the probability of being out here is very, very low. So if this happened, now we can say it looks like something funky is going on. There's two possibilities, right? One possibility is we just got lucky when we were flipping the coin. As you saw in class today, it is possible, right? I got 72% even. Why do I write lunch? I'm clearly hungry. Or there is something wrong with the coin. So those are the two possibilities. I did put on here one last piece. If you flipped the coin 200 times and got 90 heads, you'd be looking at a p-hat. Oh my gosh, I keep grabbing the wrong pens. Of 90 over 200. This is not evidence of what we want to prove. So there's no point in continuing on. If we actually did this particular piece, we would still be doing a right-tailed test because we thought it was greater than, and we're getting out a giant probability. So nothing unusual is happening here. So there's no point in doing the pretest at all if you get out a value that doesn't actually prove what you want to prove.